See, now that we have understood what a parsec really is, we'll solve a problem based on that concept. Okay, so this is our star that we have been diagram that we have been seeing so far. Okay, so this is the star, and this is our Earth. So Earth is, as we are seeing, Earth is circling around the sun. Okay, so this. Now, what we are trying to do here is that we are trying to draw this problem on right here. Okay, so what does the problem say? The problem says that the solar system, there is a star which is 4.29 light years away from our solar system. So this is the distance 4.29. Of course, the distance has not been given in parsec, otherwise the problem would have been solved, but this is given in terms of light years. So this is the distance of the star in terms of light year. And what we have been asked to do, we want to find out the parallax. See, first of all, parallax, but not this angle parallax, not this one, not this angle. What we have been asked? We've been asked to find out the parallax when viewed from two locations on Earth 6 months apart. So, parallax when viewed from this location and this location. So, we are being asked to find this entire angle. So, this angle is, let's say, theta. Okay. We also know what is this entire distance. This distance is 3 into 10 raised to power 11 meters. Okay. So all of these data already have been given. Okay. And few things we have really understood from our discussions so far. And what are those? See, the definition of 1 parsec. We already know. What is the definition of 1 parsec? It is the distance between the star and the sun if this parallax angle is 1 arc second. So that is 1 parsec. What about if this parallax angle was 2 arc second? So we know that as the angle increases, the parallax angle increases, the distance decreases. So let's say that instead of being there, the star was only 0.5 parsec. Then this parallax angle would actually be just twice. That is what it is. So we'll just draw a dotted line to signify that. Okay. Okay. So the thing that I am trying to explain is that as the parallax angle, as this angle increases, the distance decreases. And how? But by what law does the distance decrease? It decreases proportionally. So this was 1 arc second. If the distance was 2 parsec, then this will be 0.5 parsec. Okay. So the distance is 2 parsec. That means I went further away. So if I went further away, this angle would decrease. If, as in our example, if I made the distance 0.5 parsec, then this angle would actually double. So it will become 2 arcsec. So there is a relation that we can actually derive here. And the relation is very, very simple, that the distance d in parsec is always equal to 1 by p, where p is in arc second. So if, for example, I have been told that, oh, this angle really is this half of the angle. Okay, notice that this is half of the angle that we are talking about. In this relation, we are talking about half the angle. So if the distance, if this half this angle is equal to 0.5, then my distance d in parsec would be 1 upon 0.5. Okay, in arc seconds, of course, this angle is in arc seconds, and this is equal to actually 2 parsec. Okay, but one thing that we really have to be careful is that when we are using this formula, okay, our angle, the parallax angle should be this one, which is between the sun and the earth, not between the 2 points on the earth, as has been given in this question. So that is one thing that we have to, because the thing is, this formula, this one parsec is equal to 1 arc second, has been derived by assuming this angle only, So only when we are talking about this angle, does the angle between the parallax between the sun and the earth, does this formula really hold? Okay, but we will be using that formula, so that's why it has been explained. So now that we are ready with all of these basics, let us just now solve this problem. Okay, so I'm just explaining slowly and gradually how to approach this problem. Okay, so first we will draw this line. Okay, so this line has to be drawn. So we will just draw this line. Okay, so this line comes from here and then it goes to here. So we'll just draw this line because this is important. Okay, and this line is actually equal to 4.29 light years. Okay, and this angle, this entire angle, we have been asked to find. Okay, not half of this. Okay, but when we are calculating the distance in parsec, we will be only using half of it. Okay, but for now, that is what we have been asked. And again, we will write down what we know so far, which is 3.0 into 10 raised to power 11 meters. This distance is that much. So first thing we'll do is that because our distance is in meters, we will convert this 4.29 into meters, which is very simple to do. It's very easy. So 4.29 light years means that it is the distance traveled by the light in 1 year. So how much does what is the speed of light? It is 3 into 10 raised to power 8 meter per second. So now we need some time t here, which is in seconds. So let's just convert the years to seconds. So this is 365 days. Each day has 24 hours and each hour has 3600 seconds. So this is our time in seconds. This is the speed of light in meters per second. So this entire thing is the distance covered by light in 1 year, and this has been given in meters. Okay, and we multiply it with 4.29, so we get the distance of this particular star, which happens to be Alpha Centauri. This will get the distance in meters of Alpha Centauri in meters. So we have converted this to meters. We will also we know that this distance d and this distance d, we assume them to be the same. So instead of assuming that this is a straight line, we are really assuming that this is an arc. Okay, and that assumption works because this distance d is so large. Okay, so this assumption, this straight line and this arc are really, there is very little difference between these two. Okay, so now we are also assuming that, and we know that too from our discussions, that now theta in radians, if that is the case, this our assumption holds, then theta in radians is equal to arc length, which in this case is 3.0 into 10 raised to power 11 divided by the radius, which in this case happens to be d, which is this one. So this is 4.29 into 3 into 10 raised to power 8 into 365 into 24 into 3600. Okay, this, all of this data we already have. Okay, so now we can simplify this a little. We can cancel these out, and these will also get cancelled out, and this will become really 1000. Okay, now of course this is in radians. To really understand the parallax, we have to report in arc second. So we need to convert this radians into arc second. So for that, we know that 2 pi radians is equal to 360 degree. Therefore, 1 radian is really equal to pi by 180 degrees. So first we convert our radians to degrees, but of course we want everything in arc seconds, so we'll just do it in 1 second. So we have 1000 divided by 4.29 into 365 into 24 into 3600, and of course we are converting it now to first we'll convert into degrees. So radians has been converted into degrees by multiplying by pi by 180. Okay, so 1 radian is equal to pi by 180. So these many radians will multiply by pi by 180, and this comes in degrees. Of course, degrees is not good enough, so we also multiply it with 3600 to convert the degrees into arc seconds. So now this is our theta in arc seconds. We now have it. Now if you simplify this one, this comes out to be 1.54. Okay, so our first answer is 1.54 arc seconds. So that is the parallax. We found that. The second thing that we will now find out is what about this half angle right here? Okay, because this is what we need to find the distance in parsecs, because that's what we need. So this 1.54, first I will divide by 2. So that will become our angle P. Okay, will be equal to 1.54 divided by 2, which happens to be 0.77. Okay, that is the first thing we do. Now we use this formula, very simple. Okay, so distance d in parsecs, okay, will be equal to 1 by d. So this is 1 by 0.77 parsec. If you solve this comes out to be almost equal to 3. Okay, and this comes out to be almost 3 parsec, which is a very good answer, because the distance is actually very close to the distance of Alpha Centauri is very close to 3 parsecs. So we have been able to roughly solve this problem very easily, just by recognizing a few things. So hopefully the concept of parsecs and how to compute the parallax angle is very simple, and at the same time this relation is important. You should remember this, that if the parallax angle between the sun and the earth is given in arc seconds, then if I take inverse of it, reciprocal of it, I will get the distance d in parsecs.